In a lot of ways, when we were working with vector valued functions, we were relying on prior knowledge. It didn't always seem like it because of the notation. Sometimes it just seemed vastly different than what you had seen before, but it was really reliant on the same underlying concepts that you had become familiar with over time, right? When we talk about functions, we talk about continuity, we talk about limits, we talk about derivatives and antiderivatives. No different when you get into functions of several variables, so more than one variable. So we kind of go back to basics here and say, all right, well, we got to talk notation, we got to talk about domain, we got to talk about continuity, and then we get into things like limits and derivatives and antiderivatives. Okay, so a little set of bullet points there. It's all pretty straightforward stuff. The one thing that's new and unique is now it's function f of x comma y, right? Because it's a function of two variables. GeoGebra is going to be pretty useful, a useful resource when it comes to this, because of its three-dimensional capabilities. Okay, so I'm going to open that. And it's kind of a pain to do it with the app. Oh, excuse me, on a touchscreen, but I'm going to do it anyway. All right. The function of in three variables, function of two variables, we designate that as f of x comma y, but we can also set that equal to z, right? Because it's going to spit out the dependent variable z. To make things a little less complicated, we tend to write z equals, when we use GeoGebra, so z equals y times the natural log of negative x. And you can see what we're up against here, something that's a little out of the ordinary. It has a lot of kind of a look and feel, if you have a downward view, of like a hyperbola, but in three dimensions. All right, so it's projected outward into the third dimension. Coming up with the domain and range, well, not really the range, but the domain for something like this can be pretty tricky. But if we go by the important components in the function, it makes things a little bit easier. All right. So we have two factors here. One of them's y, and the other is natural log of x. We're just going to look at them individually. All right. So y could be anything. Doesn't matter what y is. It's everywhere continuous, and therefore its domain is all real numbers. So I could say y belongs to the set of reals, but it's the x part that I care about, because that's how this whole thing's going to get restricted. Right? So what I would do is I'd consider a natural log function and say, well, you can't take log of 0, you can't take log of a negative number. So whatever is contained within the natural log, I want that to be greater than 0. Okay? So that's what I'm going to do. I'm going to say negative x has to be greater than 0. Divide both sides by -1, you get x is less than 0. All right, we flip the direction of the sign. So now we have our two relationships that came from this. Now it's just a matter of stating it in the appropriate form. All right, so the way we represent this is with an open squiggly bracket. Indicate what the variables are, x comma y, vertical line. So that's the given. So our variables are x and y, given that x is less than 0 and y belongs to the set of real numbers. All right, because there's both of those things happening concurrently. that allows this function to exist. All right, so that's my domain. All right, so we look at it a piece at a time when it's in factored form. Sometimes it's not in factored form. You look at number 2. We got a radical. We have a denominator. 9 minus x squared minus y squared. Whatever that yields as an expression, numerically, whatever that yields, well, it can't be 0, otherwise it's undefined, and it can't be negative, otherwise it's imaginary. So what I would do is I would take the 9 minus x squared minus y squared and make that greater than 0. Now I can clean this up a little bit. I can subtract the 9 from both sides. But then I can negate, which would cause a direction change in the inequality. So I would say x squared plus y squared is less than 9. All right. So what that represents is a conic section, but specifically the innermost part of that conic section. All right, let me just show you in Desmos what that would look like. All right, it's a filled in circle. All right, if it were greater than 9, the shading would be outside the circle. All right, in this case, it's less than 9. All right, so this is a set of constraints. This function only exists in cases where the sum of the squared values is less than 9. All right, so for my domain, squiggly bracket, x comma y, such that, or given that. Now this one's a little bit easier to write in its final form, because unless you want to solve each of these equations for x and y, solve the inequality for x and then separately solve it for y, your better option will typically end up being just leaving it in the standard form for the conic. So my domain is that I have the two variables x and y, but specifically in the case that the sum of the squared values is less than 9. Right. We can take a look at the picture. And so that's what we're looking at. And you can see, you know, it's not perfect, but it gets the job done. You can see that the base here seems to be circular. And, you know, if you start counting boxes here, that rectangle's 2 units. It's not a stretch to say that, okay, maybe the furthest we can go out is 3 units, but it's going to create a cup. Right? So it kind of lends itself to what we were just talking about. So zooming out even more, you can get a better view. So just something to consider. GeoGebra is a good resource when it comes to this. You know, it more than makes up for the fact that it's a royal pain to use when it comes to the, you know, just actually physically typing stuff in. But, you know, it does pay off in terms of the visuals that we get. Okay. The last one is cosine x plus z and xy. Now, this is a function of 3 variables. Okay, so I'm saying here, x comma y comma z and I'm looking for a relationship between x, y, and z. Now, the numerator makes it seem like this is going to be really complicated because it's got that trig function, but cosine functions are everywhere continuous. So there is no domain restriction there. The only restriction would be if I put values in for x or z that were not real. Right? But if I'm limiting myself to the real number system, that ends up being irrelevant. So just looking at the bottom here, you see I have an x and a y, two factors, x equals 0, y equals 0. Right? Those would be my two restrictions. Right? Just like we were talking about in number 1, what x and y could be, here I'm talking about what x and y really can't be. So if it's a restriction, I'd put a not equal symbol. There's a couple ways you could represent this in terms of the domain. You can talk about what x can be, but you could also talk about what it can't be. Right? So here we would say x, y, z such that x can't be equal to 0 and y can't be equal to 0, but z could be anything. Right? So, and z belongs to the set of real numbers. Right? And that's because there was no value of z that would have caused a break in the graph or a break in the domain. It becomes even more important to be able to do stuff like this by hand because, yeah, GeoGebra can give you a sense of what the graph ought to look like, but if you're going to be able to parse through and say, oh, okay, well, my domain is clearly x squared plus y squared is less than 9. I mean, like, you can get a sense of it, but I don't know if it's going to be confirmed. All right. So let's take a look at this picture. I'm going to turn off that graph. So another z. This one would be something other than z. So we typically go back to w. Oh, I'm sorry. I was going to say, let's take a look at this graph. We can't. It's 4-dimensional. This is a 3-dimensional system. All right. So it's not going to work. All right, so for this one, you definitely gotta believe that you're doing it the right way. But what you can do is assume a constant value for z and plug it in as a function of x and y, and at least verify the xy part. So I'll show you a little nifty trick here. I don't know. It's not really a trick. It's just, you know, math. But it's kind of a cool workaround. So cosine. I'm going to put x plus a. Oh, wait. Sorry. We've already used a. I got to use a different constant. C for constant. And then xy on the bottom. So what that does is it gives me a slider because I used a constant value. Get rid of this. So it allows me to manipulate the value for C. You know, I could just play around with different values. This is my third dimension out of the 4 dimensions available. So, well, yeah, I was correct in saying that. I usually say that one backwards. But yeah, it's the third dimension. If we have 4 dimensions to work with, this is the third dimension. Right? So looking at this, we can see that it's, for lack of a better term, it's a god-awful mess. Right? If you're going to look at this graph and say, well, clearly x and y can't be equal to 0, just by looking at this, it's like, yeah, if you could ever zoom in enough to see it, sure. You know, it starts breaking apart once you do that. Right? So this is really what we're up against. Yeah, x and y can't be equal to 0, but z could be anything. Right? So this is telling us that x and y could be anything other than 0. Right? But z has no restrictions. So these little waterfalls down here, you know, that little curve downward, that looks like it's going to be asymptotic with some kind of plane, but to be able to pull that from the graph just by looking at it is definitely challenging. And so the analytic approach ends up being the way to go here. So brings us to the concept of limits. Limits is just a natural extension of the discussion of continuity and domain. Good news is limits can be as simple as they've always been, which is just quick plug and chug, but sometimes they're more complicated. Right? So I'm going to pop in this first graph here and just show you. We start off pretty simple. If I can get this dang thing to, okay. Yeah, I just want to tap on the 3 dots, but it won't let me. All right. I can't tap on anything to clear all. Let's see. Okay, so we pop in this function. Z would be equal to the fraction 2x squared y plus 3xy over 5xy squared plus 3y. All right. So that's what our function graphs to, assuming I typed it in correctly. Now it's just a question of, okay, well, what does that give us when x is equal to 2 and y is equal to 1? Sometimes it gives a nice clean answer. Sometimes it doesn't. All right. If you want, there's nothing wrong with just playing around with the notation here. And watching your iPad crash. That's always the fun part. Oh, it's preparing my library for a faster experience by crashing. Ay, ay, ay. Try to do that as fast as possible. So you see what I did? I mean, I didn't really narrate it while I was doing, but you see how I typed in, or I was typing in, f of x comma y, and it auto-corrected it to z. Oh, fun fact, this is an answer to one of the questions on the test. Oh, where did my note packet go? No, there it is. So it auto-corrected to give me function f where z is equal to whatever. All right. And so what I had erased was a colon z equals blah blah blah. So it defaulted to calling the function a of x comma y. All right. And if you can live with that, that's fine. If you need it to be in terms of f for consistency, then that's an adjustment too. All right. But what you can do is type in f of 2 comma 1. And it'll spit out a value if it exists. All right, in this case, 1.08. All right, so that would be the same as saying, let me take my x values, a little thing there, all those x values, and replace them with a 2, and then take all those y values and replace them with a 1. Two, 2, 2, 1, 1, 1, 1. And we could have factored out a y and canceled it, but it wasn't a big deal to do the number crunching anyway. So on the top, we got 8 plus 6 is going to be 14. 2 squared times 2, and then plus another 6. Then on the bottom, we're looking at 10 plus 3 is going to be 13. All right. So GeoGebra rounded it but it's an approximate value. It's only spitting out the approximation of it. All right. So when I type in 14 over 13, it gives me the approximation of it. All right. But it's a real answer. It exists. So that's great. So sometimes limits could be that easy, where you just pop in the values and see what you get. Problem is, if you remember from Calc 1, that was like one question. Everything else is like, you got to do something, whether it was algebraic or graphical. You had to do something beyond just substituting it in. So when we look at the first practice problem there, we can go after it with the same approach, which is to say, replace all my y's with 0. The x's get replaced with 1. So 1 plus 0 minus 1, that's 0 over 0. That's indeterminate. I can't write. I don't even know why I tried going script there. All right. Now, that in and of itself means that the function could have a limit that exists or not exist. You just have to do more work to uncover the reality. All right. So we need to, the directions say pretty clearly, show that the following limit does not exist. So that's telling us that we got to do something. All right. And so that something is entirely up to you, but there are ways that you can approach this that'll make your life a little easier. All right. So what I'll do again is I'll create the graph. Z equals y up top, x plus y minus 1. All right, so that's what the surface looks like. That's what the graph looks like. Okay. And at the point 1, 0, corresponding with some z value, they're saying that the limit does not exist. All right. So if you read the blurb there, you realize that there's a little bit more to limits in 3 dimensions than there is in the 2-dimensional coordinate system. And that has to do with the fact that when you're finding a limit using 2-dimensional systems, you can come in from really 2 directions. If you're finding the limit with respect to x, you can come in from the left-hand side or you can come in from the right-hand side. All right? And whether those 2 paths met or not determined whether or not the limit existed. All right? But in the case of a 3-dimensional graph, you could have infinitely many approach vectors, right, to a particular location. So what that means is we can't just say we're coming in from the left, we're coming in from the right. What we say instead is that we're coming in along a particular path. Right? And that path could be whatever you want it to be. It could be some sort of function. It could be a single plane. It could be a paraboloid. It could be anything. All right. So now, when you start getting into using 3-dimensional systems as your approach vector, that could be more trouble than it's worth. But in the case of a 3-dimensional graph, we typically want to work with 2-dimensional functions to allow our approach vector, allow for our different approach vectors. So what we do is we determine or decide upon a few different approach vectors that we think are reasonable. And if we get limits that do not coincide with one another, no matter what direction you come in from the left, from the right, from an oblique direction on either side, from obliquely from the left, obliquely from the right, if every single one of those approach vectors lead to the same point, then your limit exists. If any one of them fails to go to that location, the appropriate location, then the limit does not exist. Right? So that's what we're going to do here. I'm going to decide on an approach vector. So I'm going to approach along the plane x equals 1. All right, and I'll show you what that looks like. I got to refresh here, it looks like. Oh, wonderful. All right. I'll type it in. All right, so that's the original function. And let me get the plane in there, x equals 1. All right, so it's hard to see. A lot easier to see than it would be if you were doing it by hand. But you can see, hopefully, that plane slices a cross section through the surface. All right, so through the three-dimensional surface. All right, and so what I can do, let me see here. I just want to get the orientation right. That's negative. I don't want negatives. Yeah, I think that this is going to be the right approach. Yeah, it's probably the best I can get. But what I'll do is I'll do a quick little snapshot. All right, so this is what the graph looks like. Just got a big zoom going on there. Everywhere that it actually intersected with the three-dimensional surface, it creates a cross section. And it's hard to see, but we had something that looks like maybe over here it cut through. It also looks like maybe it cut through over here. Then it also cut through on the other side of this little flap here, so I don't want to really get into that. But it does look like it has a little cut through, just continuing down the line here. That gray one is the actual XY plane, so I'm disregarding that. But it's cutting through over here. And so it's kind of cutting right through, but there's also that piece where it just kind of hits along that that flappy piece. Right? So the coordinate 2, 1, whatever is going to be somewhere in this neighborhood. So somewhere kind of living over here. What this is saying is that we want to follow this path. Like we're living on this plane, but specifically the part of the plane that intersects with the curve itself. So if I'm following this cross-sectional slice, then what I could say is that as I'm getting closer and closer, let's say the point's over here, I'm just guessing, as I'm working my way over towards that point, what location would I end up at, right? So much more challenging to see it in the case of, let's say, three-dimensional graphs, but it also applies four-dimensional, or any n-dimensional graph than it is in 2 dimensions. Right? So I'm just going to put that aside for now. My screen is a little too big now. I got to adjust things. Can't see all of it. So what does that tell me to do? Well, I have this original function, the limit as x comma y approaches 1 comma 0. Right? Well, I'm actually going to, since I'm assuming x equals 1 is true, I can now pare this down to the limit as y approaches 0. Because what I'm doing is I'm going to replace the x with a 1. So I'm essentially holding that x constant. All right, now we can apply some algebraic techniques here. 1 minus 1 goes to 0. And so the limit as y approaches 0 of y divided by y is 1. Limit of a constant is equal to a constant. All right. So this tells us where the graph is going. Like you're journeying along this curve, this curved surface. If you were to follow the approach vector based off of the intersection between the three-dimensional graph and the plane, then you would end up at the z value of 1. So now, okay, well, I need to show that the limit does not exist. This seems to be showing that the limit might actually exist. So let's find a different approach vector. So let's approach along a y-oriented plane. So let's say y equals 0. And you might look at this and say, where are you getting the 1 and the 0 from? I'm pulling it right from the limit question because I know that eventually I have to get to x equals 1 and y equals 0. So why not get the cross section of the plane that does that very thing? All right. Yep, here we go again. Well, just not going to look at the picture because it's going to infuriate me. So what we could say here is limit as x approaches 1 of 0, because we're holding y constant at 0, over x plus 0 minus 1. Now, regardless of what the bottom shapes out to be, as long as it doesn't end up being undefined or anything along those lines, it does appear that we're going to get a 0. I put a 0 there. It should be a 1. Limit as x approaches 1 of 0, limit of a constant is equal to the constant. All right, so we work it algebraically first before we apply the limit. Because if we plug that 1 in, then we would have gotten indeterminate again. But the thing is, if we plugged in the 1 immediately before doing any computation, algebra, that would have been assuming that both x and y are variable quantities, and it would have not served the purpose of holding one of them constant, right? But ultimately, we got what we were looking for because 1 is not equal to 0. Fun fact of the day. So 1 is not equal to 0. Therefore, the limit does not exist. All right. We'll get to another example in a minute, but if those two values ended up being the same, then I'd have to find a different approach vector. All right. And so that could have been a little spicier, but you'll see spicy in a few minutes. All right. So that brings us to 52, or that was 52, 53. And you see in both of these cases, it's show that the limit does not exist. All right. And you can see that the surface there makes it, like this is the best view that I could get from GeoGebra related to this graph. So I could put it in and try to, finagle it to make it look nicer, but it's never going to be any nicer. Right. So, but I will show you what it looks like across the different approaches. Right. So, like I said before, sometimes it's just an easy problem where you can plug and chug away and come up with your answer. But regardless of how much you want it to work, this one is still going to be 0 over 0, which is indeterminate, which means we got more work to do. All right, again, 0 over 0 does not mean the limit does not exist. It means that the limit could exist. You just have to do the work to get it. All right. So what we can do is we can do our different approaches here. So I can approach along x equals 0, and I can approach along y equals 0. All right, so I'm replacing all of my x's with zeros. So it becomes the case where I'm holding x constant. So it would just be y approaching 0. So 0 times y over 0 squared plus y squared. And for the other one, I'm holding y constant, so it's x is varying. So x times 0 over x squared plus 0 squared. Okay, we can clean this up. You get 0 on the top in both cases. And so when we apply our limit, we get 0 each time. All right, so that was no help, because that seems to kind of support the opposite of what we're trying to do. We're trying to show that the limit does not exist. This seems to be kind of a blueprint or a roadway to showing that the limit does exist. All right, but what it's also telling me is that simply creating paths that are related to planes isn't going to get the job done. All right, so we got to do something else. So what we do is we kind of think of a different type of function that could represent a path along this this surface. All right. The path, again, it could be a planar path, meaning, x equals 0, y equals 0. But planes come in all different forms. It could be something that's not necessarily parallel to an axis. So. Or parallel to an XY plane, XZ plane, or YZ plane. So it could be something like 2x plus 3y minus 5z equals 17. That's a possibility. I don't know that we want to go that crazy. But we can look at, if I'm talking about lines or curves that create a path along this function, one way I can do it is look at just a parametric form of a linear equation. All right, so what I could say here, for example, is maybe you can kind of decide what you want, but let's say I'm doing an approach where parametrically it still would be a plane, but the x and y values would be going off in a different direction other than parallel to an axis. So let's say that we're going with a plane of x equals t, y equals t. So it's a vector valued function where z can be anything. So z is a free variable. All right, so this is still a plane, just like the other ones. The x equals 0. X equals 0 is the plane for all values of z, right? So, or y and z. So that gives that rectangular look, but it's locked on the x value of 0. Y equals 0 is a plane for all values of x and z. Here I'm restricting x to be in the form, x and y are linear, right? So they would form or follow the line y equals x. But I'm giving this infinite height, right? So it's still a plane just going off on an angle, right? So we play that out and see how it goes. So going back to my original function, and I'll rewrite it here. We have limit as xy approaches 0, 0 as x, y over x squared plus y squared. Here, what I would be doing is replacing every x with a t. and every y with a t. And that goes for the limiting component also. All right, so let me show you what that would look like and how we could streamline it a little bit. So this would be the same as saying limit as t comma t approaches 0 comma 0. All right, we'll change that in a second because that's a little overkill. It's saying the limit as t approaches 0 and t approaches 0. Well, isn't that the same as just saying t approaches 0? It is. So we could just write that with a single t. All right. Then we'd have t times t over t squared plus t squared. So this is the same as saying the limit as t approaches 0 of t squared over 2t squared. Which simplifies down to the limit as t approaches 0 of 1/2, limit of a constant is equal to a constant. And so we could say 1/2 is not equal to 0, therefore the limit does not exist. All you need is that one counter example that doesn't agree with the other two cases, and you have it. All right. Now, the question I almost always get is, okay, that sounds great. How did you know x and y should be equal to t? Why not something else? And the answer is, you got to start somewhere. And that's not a cop-out. That's more like, all right, well, let's go from the ground up. We want to start off with simple planes, right? X equals 0, y equals 0. It's as simple as it gets. Then if we wanted to jazz it up, I could try x equals 1, y equals 1, x equals 20, y equals 20, x equals -14, you know, and so on. I could do all those numerical cases, but I didn't have any reason to think that they would be effective. One, because I eventually have to approach 0, 0, an x value of 0, y value of 0. And also, if a relationship exists for one type of equation, it's probably going to exist for other types of that same, other variations of that same type of equation. Words. Anyway, so we graduate to the next level. All right, so after you draw an XY axis when you're first learning about graphing coordinates, next up was plotting points. Then after that, it's like graphing simple horizontal and vertical lines. But then you got into the ones that had slopes and y-intercepts, right? But the very first one that you dealt with was the line y equals x. So it was as good a place to start as any. All right, that's what we're looking at. All right. So number 3 is along the same lines. You pop in a 0, and you get 0 over 0. And again, we're looking for different approaches, different ways that we can get to that location, right? So approaches. I just write singular. So we could try the approach vector x equals 0. We could try y equals 0. We could try the vector valued function that we used before, x equals t, y equals t, z equals whatever it wants to be. Z is free. All right. Actually ends up being unnecessary, irrelevant. You don't even have to write it because ultimately it's z that we're looking for anyway, right? So it's really these two guys that you need. All right. But it's kind of hard to define something in 3 space without considering what z would be. So we're holding x constant at 0, which means y is the one on the move. Y is approaching 0. Pop in a 0 for x. You're going to get 0 times y squared over 0 squared plus y to the 4th. That's the limit as y approaches 0 of 0 over y to the 4th, which is the limit as y approaches 0 of 0. Limit of a constant is a constant. Okay, so far it's starting off almost exactly the same way as the previous one. So let's see how it plays out. I mean, it's definitely a different function, has a similar kind of look and feel, but it's definitely different. So limit as x approaches 0, x is on the move now, y is held constant, x times 0 squared over x squared plus, that's not even a plus, geez, 0 to the 4th. So limit as x approaches 0 of 0 over x squared. Same deal, limit as x approaches 0 of 0 is 0. All right, so no help there. So now we could try our nifty new maneuver of replacing x and y's with t's. All right, so that would make limit as t approaches 0. So I'm cutting out that middle step of t comma t approaching 0 comma 0. Kind of a wasted step. Replace the x's with t's. Replace the y's with t's. And see where that gets you. So limit as t approaches 0 of, well, we can factor if we want. It might be the way to go because each term is divisible by t squared. So it would be t over 1 plus t squared. Now, I've simplified as much as I can. At this point, I have no choice but to replace the t's with zeros, in which case I get a result of 0. So my nifty new move, it was a good thought, but it didn't get the job done. And I'm just going to move it down there. So we need another relationship. All right. So we tried the simple planes. We tried a little funkier plane. I mean, we could get even funkier if we wanted to do something like x equals t plus 1, y equals t minus 1. You know, but it really wasn't so much a matter of the values themselves as much as the powers, because I still ended up with a t on the top and a t squared on the bottom. If there's some way that I can consolidate all that, that would make all the difference, right? So I'm going to choose a different type of function, right? So we started off again with the constant functions, then we got the linear function. Next up on the list would be parabolic or quadratic, you know? So it's just a question of, is it going to be x equals t squared or is it going to be y equals t squared? Right? It's really a matter of preference. If it doesn't work one way, you flip it around and try it the other way, right? So let's say that x is equal to t and y is equal to t squared, where z is itself. And I'll show you how you can kind of read the situation a little bit and make the determination of what the better organizational strategy would be. So we'll sit tight on that. But I'm going to form the substitution here. Again, limit. Now, I'm going to go back to the notation here of t comma t squared approaching 0 comma 0. All right. As it turns out, we can still make the adjustment where we replace this with just t approaching 0, but not just because we feel like it. We can do it because we have the luxury of being or involving the nice number 0. Right? It doesn't always end up being the case, but because 0 is the value here, the limiting constant, we're allowed to make that substitution, right? So, and that's because if I were to solve basically t squared equals 0, that means t is equal to 0. So this is all going to streamline itself down to t approaching 0. All right. So I could do my substitution, t going in for x, t squared going in for y. All right. And again, we're still looking to simplify and go from there. I can clean it up a little bit, but eventually we're going to want to factor anyway. So let me just do that. So it'd be t to the 5th up top. And on the bottom, t squared plus t to the 8th. All right. And then when I factor out the GCF, it's t to the 3rd over 1 plus t to the 6th. And so this is a big F because I still make the substitution and I still end up with a 0. But it's a step in the right direction, which is kind of surprising to think about. But this is actually the right move, just the wrong ordering of X and Y. But sometimes you don't know that until you get started on the problem, right? So what we would do is we would try X equals t squared and Y is equal to t. Again, Z is equal to Z. You'll see a lot of similarity here between what we're doing now and what we just did. In fact, I can cut out a lot of the fluff. That's typically what we like to do. So I would say limit. Oh, you know what? I can do this in red. Limit as t approaches 0. X gets replaced with a t squared now. Y gets replaced with a t squared. When you simplify, you get t to the 4th over t to the 4th plus t to the 4th, which is t to the 4th over 2t to the 4th, which is the limit of 1/2. Limit of a constant is a constant. Result 1/2. And so we could finally say, therefore, the limit does not exist. So 1/2 is not equal to 0. Therefore, limit does not exist. All right. So that's a lot of work with not so much of a payoff. You know, it's kind of frustrating because it's like, oh, couldn't we gotten that easier? Well, a little bit. You can kind of cut out some of the trials. You do need to show that the limits are not equal. So you need one of what we did at the top there, x equals 0, y equals 0, or one of the other two. You need to show what the limit can be under some circumstances and what it can be in other circumstances and show that they're not equal to one another. All right. But the big question would be, how could I have gotten to this relationship much quicker? And it goes back to just analyzing the fraction. If you just take a look at the bottom, and this is the key to everything. We want to add these terms. We want to add these terms. So the powers have to be equal. So all we would have to do is figure out a substitution in terms of t for both x and y that would allow the powers to become equal to one another. All right. So what I like to do is just kind of rewrite one of them as a power of the other. So this is the same as saying, and this is assuming that you don't just see it, you know, just by looking at it. This is the same as saying x squared plus y squared squared. All right. So, and I'll even do the parentheses thing over here. All right. So this is our relationship, believe it or not. We would determine that this and this need to be equal to one another. So therefore, x has to be equal to y squared. All right. Now, parametrically, it's easier to define t as being equal to the independent variable. And x would be dependent on that. All right. So if I'm looking at x equals y squared, I would look at first this relationship, y equals t. Right? I should put the arrow there. And then from there, I kind of work my way back to the other one. All right? Because that's just a quick substitution. I would say, okay, I'm going to let y equal t. And so what do I get as a result for x? X equals t squared. Right? But that comes from the idea, that, like that first notion that we wanted those two powers to be equal so that we can combine those terms. All right, so this video is running long, so let me stop this recording.